Hi folks, welcome and thanks for tuning in. Today we're going to do a retro computing project and we're going to talk about ROM switchers and EPROMs. As you can see here, I have some of these old school EPROMs. I've got a programmer, some schematics, and some of these circuit boards that I put together, which we'll take a look at later. So what's a ROM switcher? Well, you've probably come across this in the past, and here are a couple of examples that you may have seen at one point in time. This Atari 2600 cartridge implements a ROM switcher via the switches that are on the surface of the cartridge. And basically what these switches do is they just let you select one of the 8 games that are available inside the chips or inside the ROMs that are stored inside this cartridge. There are 3 switches total, and when you mix and match all the combinations, you can get 8 games out of this one cartridge. Now you'll notice that this cartridge also has slots for 2 additional switches, so that would bring us up to 32 different games if those switches were implemented in some other implementation of this cartridge. And in fact, I've even seen one that has 7 switches total, giving you a total of 128 possible games. And here's another example of a ROM switcher that's very common in the Commodore community, and that's Jiffy DOS. Now, Jiffy DOS itself doesn't need this switch to operate properly. It's merely there to switch between the default stock kernel that Commodore produced and the Jiffy DOS kernel itself. So by toggling that switch, much like in the Atari 2600 cartridge, you're getting 2 different versions or 2 different types of cartridge or ROM image that's available to the computer at runtime. So in general, a ROM switching circuit like this one lets you take an EPROM that has multiple versions of the software that's stored on the computer, and then lets you use a switching mechanism via a pin header or physical switch to select one of those 2 versions. Another way to describe that is that you don't have to modify the underlying hardware to switch the version of the software or instruction code that's inside your EPROM. We'll take a look at these 2 circuit boards in a little more detail later, but in the meantime, let's look at an example of how a ROM switcher might work in the context of this 2764 schematic. So let's imagine that your hardware uses a 2764 style of ROM to store its internal instruction code. The pin layout for the 2764 is right here, and the 2764 is an 8 kilobyte ROM image. And then what happens is, let's imagine that you have a 16 kilobyte image, so this would be a 27128, and you loaded a version of the ROM on here, and then you took this chip and you stuck it in your hardware and turned on the computer. The question is, what would happen? Well, first of all, the nice thing about the 27128 is that it is pin compatible with the 2764. That means all of the address lines from A0 to A12 and all the data lines from D0 to D7 are in the exact same place, as well as the power and ground lines. And we'll take a look at that in a little more detail in a second. But then the second thing that would happen is, well, it depends on where the instruction code sits on this chip. So let's draw a small picture here to demonstrate that. Let's say that this green box is basically the entire memory space of the 27128. I'll put that down here, 1, 2, 8. So this is a 2 times 8, that is a 16 kilobyte image, and we know that this is 8 kilobytes. So your hardware can only see 8 kilobytes, and more specifically, it can only see the first 8 kilobytes on the chip. So that would be this section up here. Okay, this is 8 kilobytes, and this is 8 kilobytes down here. That means the second section is completely invisible to the hardware. And if you got lucky and you put your instruction code in the first 8 kilobytes of this image, then when you turned your computer on, it would work as if you had the old chip in there. If you had put your instruction code in the higher 8 kilobytes of memory, then the first 8 kilobytes would be empty, or they might have something else in there, and the system would probably just not work at all. So the question is now, how do we get access to this lower 8 kilobytes of memory? We know that the 2 chips are pin compatible, so maybe there's a clever way that we can manipulate this circuit or manipulate these pins such that the system could read this 8 kilobytes instead of that 8 kilobytes when it's turned on. So the technique to get access to this higher page of memory relies on understanding the schematic of the 27128. And because this chip is twice as large as this one, then we need an additional address line to access that extra amount of memory. And that address line has been strategically placed on pin 26, it's A13. Why is this important? Well, if we look at pin 26 on the 2764, we'll notice that it was not used or not connected to begin with. So any system that uses a 2764 really doesn't use pin 26 at all. And that leaves us, human beings, the ability to control this address line manually and manipulate which page of memory we would be accessing from the larger EPROM. So how do we do that? Well, we know that this is going to take either a logical 0 or a logical 1 to select the memory page. If it's a 0, we'll get this block of memory, and if it's a 1, we'll get that block of memory. When we want to represent a logic level of 1, we use a 5-volt signal, and when we want to represent a logic level of 0, we bring the pin down to ground. So to implement a circuit to manipulate A13, we would do something like the following. We're going to have our plus 5 volts to get our 5-volt signal. That can come from VCC or another location on the board. And then we'll connect this to a resistor to limit current, and we'll connect this directly to A13. And that will give us our logic level of 1. How do we get the logic level of 0? Well, let's put a switch here, and I'll try to draw this properly. And then on the other side of the switch, we'll bring the signal to ground. So this means that whenever the switch is open, current will flow from this path into A13. It will have a voltage value of 5 volts, and the computer will recognize this as having a logic level of 1. When the switch is closed, the current will take the path through the resistor and straight to the ground. This pin will be brought down to a logic level of 0, and therefore we get access to that other second page of memory. Now, as I mentioned, the resistor is here to limit the current path into this pin. We don't know how much current this pin can sink, so it's generally a good idea to have this resistor here. And similarly, when you close this path to ground, it's absolutely required to have this resistor here. Otherwise, you create a short circuit and something blows up. So a good resistor value will be anywhere between 4.7 kilo ohms to 10 kilo ohms. And if you do the math on this, the 4.7K resistor will basically limit this to about 1 milliamp of current, and the 10K resistor will be half as much, or 500 microamps. And this here is the basis for all of these ROM switching circuits. We generally find the pin that's not used by the underlying hardware, and we slap this circuit on top of it, which allows us to manually control the value of this address line. Let's take a look at some larger EPROMs where we can apply the same circuit to the new address lines that they expose. We've already looked at the 27128, and naturally we have a 27256, which is twice as large as this one. I'll go ahead and start filling in the size of these chips. It's 16 kilobytes. Oh, that should be a beat. Let's make sure we correct that before someone points out the unit problem. So going on, this is a 32 kilobyte, not kilobit chip, and this one here is a 64 kilobyte chip. Now there are some other chips in the series which are either smaller than this one or larger than this one, but they are not necessarily pin compatible because the pin size of the 2732, which is the 4 kilobyte chip, is smaller. It does not have 28 pins. And similarly, the one that's 128 kilobytes, I forget the model number, it is bigger because it needs additional address lines which cannot fit into this package of 28 pins. So if you wanted to use those smaller or larger chips, the same technique is pretty much applicable, except you'll need an adapter circuit to make sure that you route the new pins to their correct locations or handle the missing pins accordingly. Okay, what I'll do next is I'll start putting an outline over the new address lines that are introduced in each of these ICs. So then we can compare to see what's different about each of the models. So we have A14 is introduced on the 27256, and of course we have the same A13 and A14 on the 512, but we have a new guy over here, A15. Okay, so these are all in comparison with the baseline of the 2764. So we've talked about how all we have to do to implement a ROM switcher is to replicate this circuit for every new address line that shows up in the chip that we want to use. So that's kind of a general statement. What does that really mean? Well, we've basically used the 2764 as the base case. What happens if our system has a 27256 style interface and we want to use a 27512? Well, the only new address line that differs between these two chips or these two footprints is A15. So we would implement this circuit on A15. Similarly, if we wanted to use, say, a 27512 in a system that used a 27128, well, the only two new address lines that show up are A14 and A15. And again, we would implement this circuit, hook it up to A14 and A15. We would not touch A13 because the underlying system is using that, and that address line is hooked up directly to the CPU. Now, I've mentioned several times that these are all pin-compatible chips, and if you pay close attention, you'll notice that some of these address lines, they replace pins that presumably do something on the smaller size chip. So let's take a look at the 27256, for example. A14 is on pin 27. And if you look at the 27128, well, this is not a non-connected pin as it was when we looked at the 27128 and the 2764. But this is a inverted PGM signal. This stands for the programming signal. And again, if we look at the 27512, specifically address line 15 on pin 1, you'll notice that that is replacing a VPP on the predecessor chips. So what's going on here? It really doesn't look like these are pin compatible anymore. But in truth, they really are. And that's because these pins that have been moved around and repurposed, like PGM and VPP, they have been moved to a different location in the sense that those pins are only being used during the programming phase of these chips. And while the programming phase is no longer pin compatible, that's okay because the protocol for programming these chips is encapsulated in the firmware or the software that runs your programmer. When you operate one of these things, you have to tell it exactly which chip is going to be programmed. And so if you're programming a 27512, it knows that the programming voltage pin is on pin 22. It will not look for it on pin 1 as in the 27256. And that's also true for the PGM signal and some of the other things that get moved around. So for reading data, all the address lines and all the data lines are always going to be in the exact same place. And therefore, for reading data, these chips are pin compatible. So that brings us to a discussion of this module, which I put together a few weeks ago. So if I had a circuit that used a 27256 in a 2764, and then later on I wanted to use a 27512, I don't want to go ahead and rebuild it and add the little footprints for the resistor and the switch and so forth. I basically just want to be able to reuse something that I already have and not have to worry too much about it. And that's where this comes into play. So let's take a close look at how this circuit works for handling all these permutations. Here's a close-up photo of the top and bottom of the ROM switching module. If we look at the top one, we'll notice we have a set of switches, which are colored black, blue, and red. And we have the corresponding current limiting resistors for those three switches, which are all 10K in value. Each of the switches controls either address line A13, A14, or A15. So obviously we can't always control those three address lines. Our system and our EPROMs might come in different combinations, which require a subset of those address lines to be controlled. And that's where the bottom part of the circuit board comes into play. We'll notice that we have three solder pads, each for A13, A14, or A15. So you guessed it, if I wanted to only bank or switch across address line A15, then I would close the solder footprint denoted B for address line A15. The other two footprints for A14 or A13, I want those to pass through as if nothing was going on with this module. And so I would close the D portion or the default portion of those solder pads as noted by the silk screen on the module. So there are several permutations we can consider here, 6 of them being useful and 4 of them being not very useful. I've got them all drawn out on this little cheat sheet for you to refer to. And if you know the system ROM type that you're interested in and the actual user ROM that you're going to put in there, so that's the banking ROM that you're going to use, then you can follow this spreadsheet and figure out exactly how you need to configure the module. The schematic diagram for this module, along with the Gerber file to have it produced, are available on my GitHub page. It's linked below, and I'll also include any other documentation on there that's relevant to this project. If you're not interested in producing one of these modules from a factory, but you're interested in having one, feel free to reach out to me or check out my eBay listing below. I may have some available on hand, but I may also have some new ones produced if there's enough interest to do so. All right, enough with the theory. Let's move on to a practical demo. I have my Commodore 16 over here, and inside this Commodore 16 is a 27128 compatible kernel ROM. Over here, I have a 27512 compatible chip. I'm going to load 4 ROMs onto this chip, and then I'm going to install the chip onto the module that I demonstrated earlier, and then this module is going to get installed in the Commodore 16, and we'll play around with it and see what happens with all the different ROM permutations. Now, because we only need 4 ROMs on this chip, I've already configured the device to operate on the 2 address lines we're interested in. So in the 27128 to 27512 configuration, we need address lines A15 and A14 enabled for banking, and we want A13 to pass through or to stay in its default configuration. Very quickly, let's look at how we would set this chip up for programming and get the ROMs transferred to it. So first things first, we want to first collect the images that we want to place on this EPROM, and I have here 3 different types of kernels that I want to experiment with on the Commodore 16. I have Rob Clark's excellent diagnostics kernel, Diag264, and then I have a Jiffy DOS kernel, and then I also have a stock kernel for the computer. I'm going to copy the stock kernel on the EPROM 2 times, only to fill in the space. You don't need to do this, you just have to remember which space is not being used, but it's a lot safer to just copy something over that space, just in case you get the pin or the switch configurations mixed up when you turn on your computer. So what I want to do is I want to take these 3 images and concatenate them together to produce a new image, which is going to be of the desired size. So I'll use this command in PowerShell to concatenate the images together. You can even open up the files in a hex editor, put them all in order, one after the other, and then save that buffer as a new file, and you'd have your image. And that's effectively what this command is doing. It's going to concatenate the Jiffy DOS image first with 2 copies of the stock kernel, followed by Rob Clark's Diag264 kernel at the very end. And then it's going to write that to a byte encoded output file, which I'm going to call SuperROM264 for lack of a better term. This file, SuperROM264bin, is the binary image I'm going to copy to the chip. So we can do that, and we can see that the file has been written, and then we can head off to the programmer, and we can just go ahead and write that file directly to the chip. In the programmer software, I want to select the model of chip that I'm using. As I mentioned earlier in the video, every chip is going to have a slightly different programming protocol, so it's important to pick the right model and the right manufacturer just so that the programmer knows how to program the chip correctly. I've selected the one for my chip, and then the next thing I want to do is I want to check and make sure that the chip is empty. So in this particular software, we can use the blank feature. The blank feature will load the chip, and in this case, we'll look at that. It's failed because there's data on the chip. So I'm going to wipe the chip before I actually proceed to write the EPROM image that I prepared earlier. And that's done. And the final step is to load that prepared image into the programmer and send it off to the ROM. And away it goes. And we're done. So this chip is now ready to be used inside the Commodore 16 via the adapter module that I showed earlier. Let's go ahead and install it. All right, I've already removed the kernel ROM from its socket, and I've prepared my module with that EPROM that we just created. Let's get this thing installed, and we'll see how we can start selecting the different ROMs by manipulating the switches on the side of the board. All right, so since there's a common ground rail across these three switches, the closed switch position indicates that the signal is basically being pulled to ground. So the 0 value will show up on the extra address lines A14 and A15 when we turn on the computer. If you remember the order that we programmed the ROMs on this chip, Jiffy DOS was first, then the stock ROM took the middle two slots, and then the diagnostic ROM took the last slot. So we should expect to see Jiffy DOS come on the screen when we turn on the computer. Let's take a look. There we go. There's Jiffy DOS on the machine. So let's turn this off and let's manipulate the switches so that we can activate the stock ROM. I am just going to casually remove the middle one and stick it to the open position. And right now, when we turn this on, we should see the stock ROM. There we go. That's the stock ROM as presented. Let's, for argument's sake, show that the stock ROM is also on the other part of the middle of the RAM or the ROM space of the chip. So for that, we have to remove this blue one. Well, it's probably easier to remove the red one as well. This is a lot easier to do if you have an external switch. I just realized that. But this is okay. I'm fine with manipulating things this way. Okay, so the second one's open. The third one is closed. This should also yield the stock ROM. And there we go. There's the stock ROM again. And finally, let's activate the diagnostic module by opening both of the switches. Okay. Oh, and there you have it. There is Rob Clark's Diag 264 diagnostic ROM. Yeah, of course, it's going to report some problems with this board because I don't have the loopback adapters installed. And I'm also using a dubious EPROM-based PLA, which is probably why we saw that initial error message come up. So there you have it. That's more than you probably ever need to know about ROM switchers, and we have a demonstration showing how one of these configurable ROM switching board works. Thanks for watching. I hope you enjoyed this presentation, and I hope to see you back soon.